Hello students, in the last session we completed sums that are from the concept of spring. Fine, so we did see sums based on the force balancing of the spring, and then we also saw sums that are related to the potential energy stored in the spring. Fine. Finally, we started seeing sums that are related towards the power and those concepts, right? So in this session we will do the entire sums that are related to the concept of power. We'll complete all those stuff. Same way we'll start seeing sums that are oriented towards the collision, fine, coefficient of prostitution and all those stuff, right? So in this session we will do the next 11 sums based on this concept that I've told you, right? So let's jump into the next question, which will be the 46th one. So in this question they have given you a particle of mass m which is driven by a machine that delivers a constant power k watts. Fine. So you are having a mass m which is driven by a machine. So you have got a machine that is producing constant power. So the power is constant, which is given by k, and because of that power, what's actually happening over here is that mass m is getting energy. Fine. So it is going to receive energy in what form is, if the particle starts from rest, the force F on the particle at time t is, so it started receiving energy, the particle, in terms of kinetic energy. Okay, so initially it was at rest, then because of that power, that from that machine it started gaining energy, therefore it started moving with certain velocity, and as usual here I'm just constantly pumping power to it, therefore the that particle is receiving constant amount of work, which means the velocity will keep on increasing. What they're asking us to find is if the particle is starting from rest, which means initially that particle doesn't have any energy into it, therefore it is at rest. So that's the initial condition over here. So initially the work done on that particle is also zero. Same way, if the particle starts from rest, what they're asking us to find is the force on the particle at time t is, which means I'll have to get the force, which will be a variable parameter in this situation, and I'll have to get the force in terms of t. Okay, so here that particle is receiving energy from that machine. That energy is that power is also constant. Got it? So I have already found a relation in the last class, which is like power that will be equal to force times the velocity. I'll use that relation. Got it? Same way, it should be obvious. Force will also be a variable parameter, and they're asking us to find how is this force and then the time is related. That's what I need to get, right? So here to solve this sum, I'm just going to get this equation, which is like power that will be equal to force times the velocity. Fine. So here I do not want to worry about the vectors over here, which will be like vector f dot vector v, because here in the situation, whatever energy that whatever power that the machine is producing is completely getting transferred into that particle. Then in that situation, obviously it is not getting dissipated to any other form or to the surrounding. Therefore, whatever energy that the machine is producing is getting directly transferred into the particle, which means it is going to get manifested in the form of kinetic energy. Therefore, the force vector and then the velocity vector has to be in aligned and it has to be parallel. Obviously, there wasn't any loss to the surrounding. So whatever power that the machine got generated should be transferred to the particle. So if that should be the case, there wasn't any other loss to the surrounding, then obviously vector f dot vector v, which means none other particle received that power from that machine. All the power got transferred to that one particle. Therefore, it should be like vector f dot vector v. So they both should be properly aligned. So it should be pretty obvious. Now here entire energy got transferred, therefore it should be an idealized situation. If it was an idealized situation, then these two force vectors has to be in aligned. Okay, so if it was at certain inclination, then some part of the energy would have been given to that particle, it should have been released to other form, but that's not going to be the case here. That entire energy will be stored into that particle. That particle will manifest the energy in terms of kinetic energy, right? So here power was equal to force times the velocity. So when you look at this expression, it should be pretty obvious. Whatever energy that the particle is gaining will result in the form of increase in velocity, right? As the velocity keep on increasing, then obviously force experienced by that particle has to decrease, because I know from the question this machine generates constant power. Okay, therefore the power is going to be constant. Therefore, if the velocity is going to increase, then accordingly force will decrease, right? So now I'll have to get the force in terms of time. So that's the relation that I need to find. So they, when you look at the option, it should be clear. They have given us the relation over here. Got it? So to get the force, let me go into the Newtonian mechanics. So you'll have like force, which will be equal to mass times the acceleration, right? So this is the Newton's second law. So from this equation, it is pretty clear. The mass, I wouldn't be able to change. Even if I look at the option, mass is given in the option. Therefore, I wouldn't be able to replace anything for this mass. But for the acceleration, I'll have to replace in terms of time and some constant that I'm going to get out of it. Right? So I'll have to find the acceleration accordingly with respect to the time. If I find the acceleration, then obviously I'll be able to get the relation and I'll be able to get the particular option which is needed. Got it? So to get the acceleration, what is acceleration actually? Acceleration is nothing but the differential of velocity with respect to time will give you the acceleration. So I'll have to get the velocity. So if I get the velocity, then obviously I'll be able to get the acceleration. So that will give me the force. Got it? So to get the velocity, I'll have to do one more step to it, which is I'll have to get the work done. I'll have to get the work done for this particular power that they've given in the question. So what will be the formula for the work done with respect to the power? So work done will be equal to power. Yeah, so work done will be equal to the integral of power dt, right? P dt, that will give you the work done. Here, obviously, power is a constant one. Therefore, work done will be equal to k times dt. So the limit will be from the initial time is like 0, the final time is like time t. Power is also constant. Therefore, the k will come out of the integral. You will have like kt. Now I have found out the work done. So work done is nothing but the power times that time will give you the work done. So if I'm just going to consume like some amount of power for an interval of 50 seconds, if I just do the multiplication of that power times that time interval, I'll end up getting the total work done in that given time, right? So that's the intuition that you need to know. So here that particle is receiving power from that particular machine, and because of that energy received, and because of that gain of energy, what had happened to that particle is it started moving with the kinetic energy, right? So the particle is manifesting that energy in the form of kinetic. Therefore the work done, I'll be able to plug it kinetic energy for the work done, right? So here you will have like half mv square, that will give you the total work done in the situation. Initially it was at rest, therefore initial kinetic energy is like 0. So only the final kinetic energy, that will be the total energy that the machine has given to that particle. Okay, so you have got like half mv square, which will be equal to k times t. It should be obvious, right? Now I have found out the velocity. If I just do the rearrangement, I'll end up getting the velocity over here. Therefore velocity v will be equal to root of 2 kt divided by the mass. Got it? Now I have got the velocity in this condition. Next, what I'm supposed to do is I'll have to get the acceleration. So what's the equation that I need is acceleration A, which will be equal to dv divided by dt, right? Just do the differential of velocity, you'll get the acceleration over here. So acceleration A will be equal to d divided by dt of 2 kt divided by m power 1 by 2. Okay, got it? So here I'll have to do the differentiation. Before doing the differentiation, let me take out all the constant from the differential. So you have got like 2k divided by m. So these stuff are constant, whole power 1 by 2, right? So root of 2k by m will just come out of that equation. And then you will have 2k divided by m power 1 by 2. Okay, so I'll have to do the differentiation of d by dt, and you will have like t power 1 by 2, isn't it? If I have to do the differentiation over here, you will have like n x power n minus 1, that will be like half t power half minus 1, that will give you like negative half in the power. Fine. So if I do the differentiation, you will have 2k divided by m the whole power 1 by 2, and then you'll have one more element into it, which is like half differential of this term, that will give you like half t power minus 1 by 2, right? Got it? So this is the acceleration that is needed. So now I have found out the acceleration. So if I have got the acceleration, then what I need to get is the power, right? So to get the power, you will have power p, which will, I'll have to get the force, right? So to get the force F, that will be equal to mass times the acceleration, right? So mass times the acceleration. So in this case, the acceleration will be the above equation, that will be something like this, 2k and its under root divided by root of m. Okay, and then you'll have like one more half and then you'll have t power minus 2. If it comes to the denominator, you'll have 1 by root t. Okay, so let me do the cancelling stuff in this case. So if I do the cancelling stuff, the root 2 will be cancelled with root 2 into root 2 in the denominator. That will give you single root 2 in the denominator. Got it? Same way, if I do the cancelling for the mass, you will have root m in the numerator. Okay, so that's it. Now I have found out the force. If I just plug it into a single root, I'll end up getting the force. Fine. So F will be equal to root of, you'll have like root of km in the numerator. So you've got like km in the numerator. Same way in the denominator, you'll just be left with root 2 2t. Yeah, you'll have like root 2t. So that should be the equation that I need to mark over there. So mk divided by 2. So mk divided by 2 will give you the option 3. Fine. So this will be my answer, because root of mk divided by 2, and then you will have like t power minus 1 by 2, or else this t will be inside the root in the denominator. Therefore option 3 will be the answer over here, right? This sum should be clear. You shouldn't have any doubt on the sum. So to solve this sum, what I did is I just took the main equation, which is like P, which will be equal to force times the velocity. Now I have got the power. So from that power, what I need to get is the work. So to get the work done, it's nothing but the power times the time. So here the power is constant, that therefore it will be like kT. So to substitute like work, I'm just going to plug in half mv square, because whatever energy that I gave it to it from the machine got manifested in the form of kinetic energy. So that's how I'm just going to look at that particle. So when I look at that particle, it will be in the in terms of velocity, in terms of motion. Therefore, whatever energy that I gave to that particle will be in the form of kinetic. So I just equated it with the kinetic energy half mv square. Then I ended up getting the velocity, right? What they're asking us to find is actually the force. Therefore, I'll have to do the differentiation of that velocity. I'll get the acceleration. Now I have found out the acceleration. Mass times the acceleration will give you the force, right? So that's how you need to solve the sum. You shouldn't have any doubt on this question. Let's move on to the next one. Next question is a simple one. Let me read it. You have got one coolie takes 1 minute to raise a suitcase through a height of 2 meters, but the second coolie takes 30 seconds to raise the same suitcase to the same height. Fine. What they're asking us is to find the power of two pulleys, or in the ratio of. So I'll have to get the ratio of these two pulleys in terms of power. Okay, so what will be the formula for the power? Just simple, straight away sum. What will be the unit for the power? Power will be equal to work times that work divided by time, right? Here in this case, for the first coolie, he raised the suitcase to like 2 meters, but the second coolie raised to the same height, the same suitcase. So in this situation, the work was same with respect to both those coolie. Only thing that's going to change over here is the time. Therefore, I'll have to take the ratios P1 divided by P2. Work will be like constant. Therefore, it will get cancelled out. So the time will be the parameter that will determine the power in this case, right? Let me do it. One step, we'll get the answer. So here you have got like P1 divided by P2. That's what I need to find over here, which will be equal to work divided by the time. So the work over here is constant for both those coolies. Therefore, work divided by the time over here is like 1 minute in the first case, which will be equal to 60 seconds. Okay. So in the second case, you will have like work done divided by the time, that will give you like 30 seconds. Fine. So in this case, both those time should be in the same convention. So if it was in minutes, then it should be in minutes in both those situation, or it should be in seconds. Fine. So generally, if you get the confusion over here, always substitute it in SI units. You'll end up getting the correct answer, right? Do not want to confuse over here. Just substitute it in SI units. You'll get the answer straight away. So half work done will get cancelled out. 60 and 30 will get cancelled out, and then you are just left with 2 in the denominator of this first term. So okay, so P1 divided by P2, P1 divided by P2 will be equal to 1 divided by 2. So the answer over here is like 1:2, which is like option 4, right? This sum should be easy, right? So just if you look at the statement, it will be pretty obvious. The first coolie takes like 1 minute, the second coolie takes like 30 seconds. Then obviously the second coolie has the more potential to do work quickly. Therefore, this coolie should have greater power when compared to the first coolie, right? Because the first coolie is taking more time to do the same amount of work, but in the case of second coolie, he is just doing the work quickly. Then obviously the power of the second coolie has to be greater when compared to the first coolie. So when you look at the option, it is pretty obvious. It should be like 1:2. So second coolie could do 2 times greater work when compared to the first coolie, right? It should be clear. Let's move on to the next one. Next sum is also the same kind of sum that you have seen earlier. Let me read the question. Just 2 steps, you'll get the answer. Here you have got a car of mass m starting from rest and accelerates so that instantaneous power delivered to the car has a constant magnitude of p naught, which means there is a car which is initially at rest. Fine. Consider it to be like a particle which is initially at rest. Then engine starts pumping power into the tire. Therefore, the engine is running at a constant rate, which means the power produced by the engine is constant. That was equal to p naught. Fine. Then what they're asking us to find is the instantaneous velocity of the car is proportional to. So here I'll have to get the velocity, right? This is a kind of sum where if I just do the first part of the sum that we have done earlier, I'll end up getting the answer, right? Straight away sum, you'll get the answer. So here you have got constant power. So this stuff is actually producing constant power that was equal to P naught. So what will be the power? It should be equal to work divided by the time, right? So work done divided by the time, right? Just do the cross multiplication. Work done will be equal to P naught times T. Do not want to do the integration because P naught in and itself is constant, right? I'll be able to substitute kinetic energy in the place of the work done, right? So same kind of logic that we have already seen. So in this sum, let me plug it half mp square in for the work done, which will be equal to P naught times T, right? So P naught times T, right? What I need to get is actually the velocity V. So the instantaneous velocity of the car is proportional to, they're just asking the proportional thing over here. So velocity V will be equal to how is the velocity and then the time is related. That's what I need to get over here. So that will be like P naught T 2 P naught T divided by M, right? So 2 P naught T divided by M and it's under root. Fine. So here in this case, the time is actually related to the velocity is actually related to the time in terms of root. Okay, so T power 1 by 2 will give you the correct relation. Fine. So if you look at the option, there is possibility for this one and this one. But here it is like T power 1. So that shouldn't be the case. If it was like root T by M, then that will be the best match. But in this situation, only the time is something that seems to be the better answer over here. Therefore option 2 is the answer over here, right? So T power 1 by 2 is the answer. Got it? So this is a kind of easy sum. Just here in this case, I'm just finding the first part of the sum that we have already solved, right? You shouldn't have any doubt in the sum. It should be clear. Let's move on to the next one. In this question, they have given an engine pumps water through a hose pipe. So you have got a water pump which is going to pump water through a hose. Fine. Water passes through the pipe and leaves it with a velocity of 2 meter per second. So the water that is exiting from that hose has a velocity of 2 meter per second. So they have given us the exit velocity. Then what they have given is the mass per unit length of water in the pipe is 100 kg per meter. Got it? So if the mass that got ejected from the pipe was equal to 1 meter, so that 1 meter mass will have a mass that is equal to 100 kg. So they have given us mass per unit length. Fine. What they're asking is to find is what is the power of the engine. So I need to get the power of this engine. So we have seen such a kind of sum already. I hope so in the first or second sessions. Okay, so in that question, it was something like this. I'll have to get the final formula. Okay, so they in that question they have given all the condition and they're asking us and they were asking us to find the final formula. But in this question, they have just given numbers to those condition and I'll have to get the numerical value, right? So to solve this sum, first I should know the formula, right? So to get that logic behind it, you just draw a diagram such that you're having a hose pipe and then there is water that is exiting this hose pipe with a velocity of 2 meter per second. Fine. So when the total length that got ejected was equal to 1 meter, in that situation the total mass will be equal to 100 kg, right? So what they've given over there is mass per unit length. So they've given us the mass per unit length. Let me take it as small m. So small m will be equal to the total mass that got ejected divided by its length, which should be equal to 100 kg per meter. Fine. So if the total length that got ejected was equal to 1 meter, then it will be equal to 100 kg of mass that got ejected. If it was like 2 meters, then it will be equal to 200 kg. Okay. So that's how it will get related. Now what they're asking us to find is actually the power of this water pump. So the power will be equal to work done divided by the time, right? So in this case, work done will be the kinetic energy that was possessed by all the water molecules that got ejected, right? So every single water molecule will have a kinetic energy of half kinetic will have an velocity of 2 meter per second, right? Here what I need to find is what was the total energy that was given to that entire water element, right? So that will be equal to half the total mass that got ejected times the velocity square, right? So work done should be equal to half, right? So the total mass that came out of this exit pipe will be capital M. Okay, so that was the total mass that ejected. So that should be equal to the total mass, which will be like capital M, and the velocity of this entire water element was equal to V square divided by the time. Got it? So now I'll have to replace this total mass by mass per unit length. So total mass will be equal to mass per unit length times the length, right? So ml, small m times capital L will give you the total mass that got ejected. Therefore, the next step will be half. Instead of capital M, you will have mass per unit length times the total length that got ejected into velocity square divided by the time. Fine. Same way in this question, the total length that this particular initial mass has covered divided by the time will give you the velocity, right? So the length that it has covered from the exit divided by that given time will give you the velocity of this water molecules. Okay, so that should be equal to 2 meter per second. So length divided by time will give you one more velocity term into it. Therefore, power will be equal to half times mass velocity cube, because L by T will give you the extra one more velocity. So V square into V will give you the V cube. Fine. So this is the formula for the power. Let me substitute all the numericals that they have given in the question, which will be like half mass was equal to mass per unit length was equal to 100 kg per meter. So this small m is actually mass per unit length. So 100 kg per meter times V cube. What should be the velocity in this case? It should be like 2 cube, right? So if one of the two get cancelled out, you will have like 2 square, that will be like 4. 4 into 100 will give you 400 watt. So the answer over here is like option 1, which is like 400 watt. Fine. You shouldn't have any doubt on this question. We have seen already this kind of question in the first session itself, right? In that question, I just found out the formula, but in this question, they are just asking us to plug in some numbers into it and get the final answer. That's it, finished. Right? So you should know this formula by heart. Then it will be like handy, which is like half mv cube, where small m is actually mass per unit length, right? So that's the understanding and notion that you need to know. Let's move on to the next one. Next one is like a very simple question, right? You have got a particle of mass capital M starting from rest undergoes uniform acceleration. Fine. So there wasn't any initial kinetic energy. If the speed acquired in time capital T is velocity v, the power delivered to the particle is, right? So here in this question, they have given us clearly it is undergoing constant uniform acceleration, which means A is constant. If A was constant, then obviously force will also be constant, right? So here in this question, they're asking us to find the power delivered to the particle. So to get the power will be equal to work done divided by time. That will give you the power, right? So power should be equal to the work done. So in this question, they have given the speed acquired in time capital T is like V. So the final velocity is something that they have given. So if I know the final velocity, obviously the energy that was stored into that particle will be equal to half mv square. Half mass was like capital M V square divided by that time. So the time also they have given us capital T, right? What they're asking us to find is actually the power. So the relation for the power will be like work done divided by time. That will give you like half mv square divided by t. So just match it with the option, you will get the answer. Half mv square divided by t, that will be like option 4. So the answer over here is option 4. You shouldn't have any doubt. Let's move to the next one. Next sum is water falls from a height of 60 meter at the rate of 15 kg per second to operate a turbine, right? So you are having a turbine which is going to generate electricity, right? From the waterfall. So the water is falling from a height of 60 meters. So the rate at which the water is reaching the ground surface is like 15 kg per second. So that much amount of water, 15 kg of water will reach the turbine per second. So that's the thing that I've given in the question. So that's the first statement. Then you have got the losses due to frictional forces are 10% of energy. So out of all the energy that is going to get generated, 10% will be lost because of the friction between the water molecule and then the rock, okay, or else other form due to the air drag force, whatever it is. So 10% of the energy got lost to the surrounding. Only 90% of that kinetic energy will be used to generate the current, okay. So that should be clear. So there is a loss of like 10%, which means out of all the potential energy that has been stored into the water, only 90% of the energy will be usable to produce the current, okay. So here what they're asking us to find is how much power is generated by the turbine. So I need to get the power of the turbine. So how much it could actually generate in the given time in per unit time. Fine. So I need to get the power of the turbine. So power will be equal to work done divided by the time, right? So here to get the work done, I know the energy got stored in terms of potential. So that potential energy got converted to kinetic, and in that kinetic energy only 90% was usable, 10% lost to the surrounding in other form, right? So I'll have to get only the 90%, which is like 0.9. Fine. So whatever energy that the water possessed was equal to the potential, that should be equal to mgh, right? So mgh, this entire energy isn't transmitted to the turbine, only 90% of this energy was usable, so that from that 90% of the energy I was able to generate the current, okay. So 10% got lost. So I'll have to account only that 90%, which will be like 0.9 divided by that time, okay. Fine. So I'll be able to do the sum. So here they have given us like mass per unit time. So here if you look here, the total mass that reached divided by that time, that will give you like 15 kg per second, because they have given us the rate straight away. So instead of m by t, let me substitute 15, and then for acceleration due to gravity, that will be 10, and then for the height they have given us 60. Only 90% of the energy was 90% of the potential energy was usable, therefore I'll have to multiply it with 0.9. 10% got lost. So just do the solving, you'll get the answer straight away. Fine. So here just leave this 10, this 0.9 will become 9, and then you have got 15 into 6 into 9, right? So that will give you 9 into 6 will be like 54. So 54 into 15, that will give you the answer, right? 20, 25, 27, and then you have like 54, 0. This will be like 1. Then you have like one more one, 810, right? So it should be equal to 810, and then you have got one more 0 into it. So 8100. Okay, so 8100, if we move the decimal, you'll have like 8.1 kilowatt. Okay, so 8.1 into 10 power 3, that will give you 8.1 kilowatt. Fine. So 8100 watt is nothing but 8.1 kilowatt. You should be clear with that convention. So the answer over here is like option 3, right? You shouldn't have any doubt on this question. Simple one. Just get the potential energy that will get converted to the kinetic energy, obviously, right? So I know the potential energy over there. 100% of the energy wasn't used. Only 90% was used to produce that current. Therefore, just multiply it with 0.9. We'll end up getting the numerator that was needed divided by the time, right? So mass per unit time was given in the question, which was equal to 15 kg. Just substitute 15 in the place of m divided by t. Just do the solving, you'll get the answer, right? It should be easy one. You shouldn't have any doubt on this question. Let's move on to the next one. Next sum is kind of vector based sum. Let me read it. you have got if vector f was equal to 60 I cap plus 15 j cap minus 3 k cap. So you have got the force vector that they've given, and vector v was equal to some vectors 2 I cap minus 4 j cap and 5 k cap meter per second. Then the instantaneous power is. So I need to get the power from this question. Power will be equal to vector f dot vector v, right? So they have given us those two vectors in the question itself. Just do the dot product, you'll get the final answer, right? Vector f was equal to 60 I cap, right, plus 15 j cap minus 3 k cap dot product with vector v, which will be equal to 2 I cap minus 4 j cap plus 5 k cap. Okay, just do the multiplication, you'll get the answer. Therefore that will be equal to 60 into 2, that will give you 120. You shouldn't put any I cap and j cap because dot product will give you only the magnitude. Just do the multiplication of same component, right? So 60 dot product with 2 will give you 120, and then 15 j cap minus 4, so that should be negative, right? Negative 4, so that should be like 60, right? Yes, minus 60, then you will have minus 15, 1 5. So if you have to do the subtraction, you will have 120 minus 60 will give you 60. 60 minus 15 will give you like 45. Therefore, the answer over here is like 45 watts, which is like option 2. So this is one of the easiest sums, right? It should be clear. The answer here is like option 2. Fine. You shouldn't have any doubt on this question. Let's move to the next one.